Bismillahirrahmanirrahim. This is Jahangir Badar Sumro, Assistant Professor, Electrical Engineering Department, Sakkara University. This is the part 2 of the video. In the first part, we have discussed about introduction portion of design and control of modular multi-level converter for voltage Sag mitigation. We have discussed up to page number 8, arm inductance. So now we'll continue section 3rd, proposed system description. All right. So this is the detailed proposed system model. It consists of an upstream grid. It consists of an upstream grid here, which is 220 kilovolt, and this YD transformer is used that step it down to 66 kilovolt. The advantages of using this YD transformer is that it eliminates the zero sequence component. As we know that if the grid becomes unbalanced, so it will result not only into the positive sequence component, but when it is unbalanced, then there will be positive sequence component, negative sequence component, and zero sequence component. So this Y delta transformer, YD transformer, will eliminate zero sequence component. So there is no need of external another separate zero sequence separation controller here in the control section. And this is a back-to-back HVDC system. This is rectifier station, this is inverter station. The DC voltage VDC link is 135 kilovolt. This 135 kilovolt is again inverted into the AC voltage VAC, which is stepped down into 11 kilovolt from 66 kilovolt to 11 kilovolt to meet the requirement of this load distribution system, 11 kilovolt dynamic. All right. Now this rectifier station is basically consisting of two outer control loops. This rectifier station is mainly responsible for controlling the DC voltage, VDC. In this case, reference DC voltage is 135 kilovolt. So 135 kilovolt reference voltage will be given over here, and this is responsible to maintain the desired DC link. The output of this outer loop controller VDC voltage controller is ID ref, and this reference signal goes to inner current control. D component of the current real quantity comes from the direct voltage control, and another outer loop control which here this rectifier station is responsible for AC voltage controller. This is the reference AC voltage. This is the measured AC voltage. A PI controller is used here, and the output of this AC voltage control is IQ reference. So D component is coming from the DC voltage control, and Q component of the current is coming from AC voltage controller. These outer loop controller give the reference current for inner current control. In my previous videos, if you are interested to go into detail of inner current control and outer control loop, you can refer to my previous recorded videos where I have discussed them in a very detailed way. Now this inner current control basically this inner current control generates is responsible to take D reference current, ID reference, and IQ reference, and it gives two components. It gives VD and it gives VQ. These are the output quantities from this inner current control. D component of the voltage and Q component of the voltage. They are again converted into the ABC from DQ to ABC transformation, and then they are fed back by using nearest level modulation or any other modulation, and they are fed back to the the gate signals to the switches over here. These switches can be IGBT or MOSFETs. Differential voltage, uh, the signals that are coming towards the inner current control is one signal is coming from circulating current separation controllers. This is to ensure that the second this is ensure that the circulating current component, which is twice the fundamental frequency component, AC component of the circulating current, is suppressed, and this signal comes from the CCAC circulating current separation control. And here we use PLL block, and we convert the ABC voltages and currents into DQ components, ABC to DQ components. Then we extract the phase angle, which is theta, using PLL. These DQ components, current DQ components, VD component, these are the inputs to this inner current control. And then the output of the inner current control goes to the pulse generation in LM, and then the gate signals are feedback to the rectifier. This is how it is working. In the same way, the inverter station is responsible for maintaining the active power, because in HVDC, if it is point-to-point or back-to-back converter, one station is responsible for DC voltage control, and other station is responsible for active power control. So this is responsible for active power control. P reference is given here. Here it is also responsible for controlling the AC voltage. So again, D component of the current comes, ID reference comes from here, IQ reference comes from here, and inner current control and the remaining portion is similar as of that of the rectifier station. So this is the proposed system model. Here, dual synchronous reference frame based current controller is developed for the current control mode. So this actually, this inner current control is basically a dual synchronous reference frame. Why do we need dual synchronous reference frame? We are discussing. Okay, this is the equivalent circuit of MMC. So there are basically 3 legs. Leg 1, leg 2, leg 3. These are upper arms. So 6 arms, 3 legs. All right. Let's discuss mathematics of this model. I would prefer to discuss mathematics from another paper, because it is better explained the same equations in a simpler way. Right. So basically this is the model. First thing that we are interested to see is AC voltage, terminal voltage AC. So if you apply KVL, you will get this equation. So if you apply KVL here or in this circuit, you will get that equation. So basically, if you apply KVL, let's apply KVL. It will be VDC by 2. So this basically this is VAU. Upper arm voltage. So this is VAU, means upper arm voltage of phase A. So this is equal to this voltage Let me take a screenshot of this. Put it here. This VAU, upper arm voltage, is equal to VDC by 2 minus this terminal voltage. So this upper arm voltage VAU will be equal to VDC by 2 minus terminal voltage VMA minus the drop across this inductor, which is L0 DI upper arm current over dt. So this is the upper arm voltage in phase A. Similarly, you can derive the equation for lower arm current, lower arm voltage VAL, which is equal to VDC by 2 plus VMA minus L0 DILA upon dt. Theoretically, we know that upper arm voltage and lower arm voltage are 180 out of phase. Therefore, you can see the signs are sign is different. Minus VMA, here it is plus VMA. So terminal voltage VMA is equal to VLA minus V upper A divided by 2. And this terminal voltage can be varied by changing the modulation index M. So you can write this equation like this as well. Now this AC voltage ideally should be equal to the DC voltage of this converter if this inductor drop is ignored. So this is the terminal voltage VA, which is equal to VDC minus inductor drop. And this is the equation for upper arm current. Now this upper arm current, upper arm current of this, which is flowing here, this consists of one fundamental component. This is basically fundamental component I8 by 2 sine omega t plus phi x plus differential component, differential current. Either it is differential current, I will explain it. So this is common mode current. Half of the fundamental current comes from upper arm and half comes from the lower arm, and here it becomes IA, terminal current of the inverter, AC current. So this is common mode current. IMX is common mode current. This is desired. And IZA, similarly for lower arm, the signs will change, minus fundamental current IA by 2 sine omega t plus phi x plus IZA, differential current. So there will be 3 upper arm currents because there will be 3 upper arm submodules, 3 upper arm and 3 lower arm. This is for one phase. Similarly, there will be IUB, ILB, IUC, ILC. And they will be 120 apart. This theta is that angle. So this is the differential current, IZA. Now what is differential current? Differential current is basically summation of both currents, I upper arm current plus I lower arm current divided by 2. If this is equal to differential current, or in other words, you can say the differential current consists of 2 components. One is the DC component. Let me explain this thing from here because it will be easier. Yeah. So here comes the DC current from this battery. Now this DC current, there are 3 legs. It will be divided in 3 parts. Half here, here and here. So this will be 1/3 here, 1/3 here, 1/3 here. So IDC by 3 here, IDC by 3 here, IDC by 3 here. All right. Okay. So this differential component current consists of 2 components. One is the DC component. This is desired component. This is desired component, IDC by 3. And other is the AC component of the circulating current, I circulating A, sine and omega t plus theta y. Basically, our purpose is to eliminate this part of the equation, circulating current. This is not desired. We need to eliminate this portion. And circulating current suppression controller is implemented in the control portion to basically eliminate and suppress this portion of the equation, circulating current, which is twice the fundamental frequency, and it is found to have negative sequence component in the case of the balanced grid. This is the equation for capacitor voltage in the upper arm. And capacitor voltage also consists of two components. One is the DC component, which is responsible for the energy storage in the capacitor. This is desired. And other is the ripple. So capacitor voltage does not only consist of the DC component, but it also consists of the ripple. This is not desired. If this ripple is increased to a very high value, then it will become an issue for stability of the converter. And this ripple component has a relationship with circulating current. If this circulating current is not controlled properly, initially it majorly consists of a second harmonic. Second harmonic is the dominating component in this circulating current. But if it is left uncontrolled, it will trigger fourth harmonic, sixth harmonic, eighth harmonic, and onwards, and it will result into the increased capacitor voltage ripple problem. So if it is left uncontrolled, this portion of the ripple will increase and overall converter will trip. So take care of these two things. It's necessary to suppress these two things. And a lot of active research is going to control these two things. These are the equations for energy. And we see from the equation of energy that basically MMC equation does not consist of only DC component and the fundamental frequency, but there is also the component twice the fundamental frequency, sixth harmonic, eighth harmonic. Major dominating factor is second harmonic. These are less contributing. So our purpose is to eliminate these multiple harmonic components, suppress these circulating currents from here and from here. All right. So this is the mathematics. Now let's come back to this paper. You are the average and difference between upper and lower arm voltages. So this is equation 22. Now basically equation 22, this is same as, this is in matrix form, and this equation is for three phase. This is basically same as that of this equation, but this is for only A phase. You can also write it for phi and C, and you can also write it in matrix form. If you put it into the matrix form, these two equations will be similar. So this equation presents the AC side of the MMC. So if you apply the Park and Laplace transformation equation on this equation 22, you will get this equation 23. Okay. If it is balanced grid, then only there will be positive sequence component, and there will be no negative sequence component, and there will be no zero sequence component. So first we are discussing with when the grid is balanced. So apply the Park and Laplace transformation to equation 22, it will result in this equation. This is D component, this is Q component. As I already told you, so if you finalize this equation, so in reference 28, this equation of inner current control is finalized here. So here from we can see that in inner current control, there are two input quantity. There are some input signals coming, like ID reference, IQ reference, and the output signals that you get out is UD and UQ, as discussed already. VD, you can also write VD, VQ. So from this inner current control, two things will be coming as an output, which is VD reference and VQ reference, or UD reference, UQ reference. There will be a PI controller, This is representing the PI controller here. PI controller ID ref minus ID. So ID ref, and this will be coming from outer loop control, either from active power control or DC voltage controller. And this is the measured current ID component. So ID ref minus ID and this PI controller. So this will be this expression plus omega L IQ, this component, plus minus plus UD. So this plus will become this expression. And similarly UQ will be this IQ reference minus IQ measured reactive component, imaginary quantity PI controller, and VQ component plus VQ plus this cross coupling omega L component, which comes due to the transformation from ABC to DQ here. So this is inner current control. All right. If it is unbalanced grid condition, so there will be positive sequence component, negative sequence component, and zero sequence component. Now, as already mentioned, this transformer YD will eliminate and reduce this, suppress this zero sequence component. But this inner current controller should be responsible now in case of unbalanced grid condition to eliminate both positive sequence component as well as negative sequence components. Here it was only positive sequence component. So this inner current control will change in case of unbalanced grid condition, and this will be called dual synchronous reference frame. And initially we had only this equation. Initially we had only positive sequence component, but now we have also negative sequence component. All right, so this is the dual synchronous reference frame inner current control in case of balanced grid. So here we will make this negative component reference 0. We'll also make this component 0. We will suppress this negative component, eliminate this negative component. All right. This reference component will be coming from outer loop control. And finally, this reference signal, which is basically UD reference, UQ reference, this reference signal will go to basically PWM, nearest level modulation technique, and then gate signals will go to the rectifier station and inverter station. This is how inner current control basically works. Now we will discuss circulating current suppression control. So I have already mentioned in my first part that we try our level best by using capacitor voltage balancing algorithms to ensure that upper arm submodule voltage and lower arm submodule voltage and leg voltages of one leg to the other leg, they should be equally balanced. They should be ideally equal. But practically there is always some difference. And due to this energy difference between one upper arm to lower arm and between three legs, this energy difference results into potential difference. And this potential difference causes current to flow between one leg to another leg, from this leg to another leg. So this current which is flowing between the legs, this is called circulating current. Let me show it from this. See, this red dotted current, this is basically circulating current. Why it is flowing? This is flowing due to energy difference between upper arm and lower arm and between one leg to another leg. Because whenever there is a potential difference, and result of potential difference, circulating current will flow. So I circulating A, circulating B, I circulating C. Our aim is to suppress this. And therefore we are using circulating current suppression control algorithms, because only arm inductor can limit this circulating current up to only a certain limit. But you also need some controller to eliminate the circulating current. So we are discussing now about that controller, circulating current suppression controller. All right. Okay. So the motto is to eliminate the circulating current. All right. How can we eliminate the circulating current? By ensuring, by reducing this potential difference, imbalance voltage. If this imbalance voltage is cancelled out, if there is no potential difference, imbalance voltage, then no current will flow ideally from one leg to another. So our purpose is to get to reduce this differential voltage or reduce this imbalance voltage. So if this impedance voltage is reduced or differential voltage reduced, then in result, circulating current will be suppressed or reduced. All right. So therefore, the output reference quantity of this circulating current is the differential component of the voltage. By controlling that differential component, which is VCC, A, B, C, these three components for three legs, you can control the circulating current. So these circulating currents, ICCA, ICCB, ICCC, can be controlled by reducing this impedance voltage, which is occurring across this inductor drop. This differential voltage should be maintained to maintain this circulating current, should be suppressed to suppress this circulating current. So let's discuss mathematics. Put it here. Put it here. So this DC, if again apply KVL, this will become VDC is equal to summation of voltage, this up with this summation of voltage plus drop across this inductor and resistor to ICC arm. This is circulating current, ICCA L arm plus 2 L arm DI circulating current CC over DT. So this summation of upper voltage can be written, will be basically summation of upper arm voltage plus lower arm voltage. So this can be written here as V upper plus V lower. The rest of the expression is same. Okay. So take 2 common, you will get ICC R arm plus L arm DICC over DT. And this in ICC arm R arm plus L arm DICC over DT is equal to VCC. You can write it VCC or V differential. So this is VCC, this will become 2 VCC. Take this term over here, from move it to the that side. So this will become VDC minus 2 VCC is equal to V upper plus V lower. So now put this expression into equation 35. So this will become VDC. Now V upper plus V lower is equal to what? VDC minus 2 VCC. So this is VDC minus 2 VCC plus we know that 2 VCC is equal to 2 R arm ICC plus 2 L arm DICC over DT. This VDC will be cancelled. Take this VCC over here, take 2 common. So VCC will become equal to this expression ICC arm, means this drop across resistor, inductance, resistance, and inductor. So if you maintain, if you balance this drop, if you balance this drop across these inductors, if this potential difference is reduced, then circulating current will be reduced. If this differential voltage will be controlled, this is what I was saying. So this will be there are 3-phase MMC. So VCCA, VCCB, VCCC. And if you convert this equation 38, 39 into 40 into DQ transformation, so you will get this equation, equation 50. So we write it into D and Q component, this equation. I mean this equation, if you convert 38, 39 and 40 into DQ transformation, this will become equation 50 here. All right, this expression comes due to the transformation from ABC to DQ. And this block diagram of circulating current suppression comes from this equation, basically equation 50. It was found out that the circulating current is basically twice the fundamental frequency, and it has negative sequence component. This is for phase A, phase B, and phase C. And it was found out that if you sum these all circulating currents, ICCA plus ICCB, ICCC, their sum will become 0. What does it mean? This means that the circulating current only flows between the lakes, and it is neither going to disturb this DC side voltage, nor it is going to affect the output AC voltage of the terminal voltage of the MMC. This will be flowing only between the lakes. This is what this equation means. That if you sum these all, their sum will become 0. Now you see that as we know that if we add upper arm current plus lower arm current divided by 2, then it will become circulating current for phase A, for phase B, and for phase C. Let me show you this equation. I upper arm plus I lower arm divided by 2. This is differential component. So in differential component, there is also circulating component. So what you first do, you add upper arm plus lower arm, you divide it by 2. Upper arm plus lower arm divided by 2, this will become circulating current, differential current for phase A, B, and C. Then you, again, what you do is that you basically so this is basically circulating current. So you convert from ABC to DQ, so this will be ID and other will be IQ. And you give a reference value to this PI controller, which is 0. Our purpose is to make this circulating current D component, Q component 0. Alright, so this equation is put into this block diagram. So here from this will give you V differential component VCCD and VCCQ. This differential voltage VCCD and VCCQ will be converted back into the ABC. And this will be resulting V differential voltage or VCC component, and that will be added into the reference signal, and then they will go to pulse generation NLM for switching signals to the MMC, rectifier, and inverse restoration. So this circulating current controller for the inverter and rectifier restoration will be the same. There will be no change in this controller. I hope the purpose of the circulating current controller is quite clear now. We'll discuss the remaining portion, description of output controller and results in the third part of the video. Thank you very much.